Uh, right. So, a very good afternoon to all. And in this session, we are going to discuss about the role of physicists behind quantum computing as a part of Science Day celebrations. So, I'm going to share my screen. All right. The role of physicists behind quantum computing. So, we have been listening through all this quantum computing aspects in these recent days. But the starting point for this quantum computing started long before, during Second World War, when the first computer was started, invented for the purpose of artillery and decoding war messages. So, in continuation to that, especially major developments in computations, computer architectures, and computer hardware came through this particle physics experiments. మనం చూసినటువంటి మేజర్ కంప్యూటర్ డెవలప్మెంట్స్ అన్ని కూడా ద కేమ్ బికాస్ ఆఫ్ ద రీసెర్చ్ ఆన్ పార్టికల్ ఫిజిక్స్. సో మనకు పార్టికల్ ఫిజిక్స్ లో జరుగుతున్నటువంటి రీసెర్చ్ like there'll be millions, trillions of particles colliding for each second, and especially we're going to get in a single experiment like a proton collision experiment lo chuste, you'll get petabytes of data for 1 second. Petabytes ante enta andi? Mega, giga, zeta, peta. 10 power 6, 9, 12, 15. So in 1 second, you're going to get 10 power 15 data points. ఇది ఒక పార్టికల్ కొలిజన్ జరిగితే దాని స్కాటరింగ్ ఎన్ని డైరెక్షన్స్ లో వెళ్తుంది. సో పార్టికల్ యాక్సిలరేటర్స్ కూడా ఆల్మోస్ట్ కిలోమీటర్స్ అండ్ హండ్రెడ్స్ ఆఫ్ మీటర్స్ ఆఫ్ ఏరియా ఇస్ ఇన్ కవర్డ్ బిల్డ్ అ పార్టికల్ యాక్సిలరేటర్. సో అంత ఏరియాలోంచి మనకు వచ్చేటువంటి డేటా పర్ సెకండ్ మనకి జెటాబైట్స్ అండ్ పెటాబైట్స్ ఆఫ్ డేటా వచ్చేస్తుంది. సో ఆ డేటాని మనం విత్ ఇన్ దట్ సెకండ్ రికార్డ్ చేసేసి పక్కన పెట్టేయాలి. లేకపోతే ఏమవుతుందంటే యువర్ నెక్స్ట్ సిరీస్ ఆఫ్ డేటా విల్ కమ్ అండ్ ఓవర్ రైట్. సో విత్ ఇన్ దట్ షార్ట్ స్పాన్ ఆఫ్ టైమ్ వీ హ్యావ్ టు కలెక్ట్ ద డేటా, సేవ్ ఇట్, అండ్ దెన్ వీ హ్యావ్ టు బి రెడీ ఫర్ ద నెక్స్ట్ సిరీస్ ఆఫ్ డేటా. ఇన్ని పనులు మనకి చాలా క్విక్ గా జరిగిపోవాలి. So that has enormously improved our computational facilities, especially the first World Wide Web was developed for this purpose. అంటే మనం ఒక సింగిల్ కంప్యూటర్ లో ఇంత స్పీడ్ గా డేటాని కలెక్ట్ చేయటము, స్టోర్ చేయటము, ఇట్ సౌండ్స్ ఇంపాసిబుల్. సో ఆ కండిషన్స్ లో ఫర్దర్ డెవలప్మెంట్స్ వర్ టు డెవలప్ వరల్డ్ వైడ్ వెబ్. ఈ వరల్డ్ వైడ్ వెబ్ కూడా CERN నుంచే స్టార్ట్ అయింది. And further we are enjoying the fruits of that. ఆ ఇంటర్నెట్ ని అక్కడి నుంచే ఇంటర్నెట్ నెట్వర్క్ ఆఫ్ సిస్టమ్స్ లో మనం డేటాని కంటిన్యూస్ గా స్టోర్ చేయడానికి, అట్లాగే ఈ ఆప్టికల్ కమ్యూనికేషన్ బిట్వీన్ కంప్యూటర్స్. సో ఆ నెట్వర్క్ లో ఉన్న సిస్టమ్స్ మధ్య మనకి ఆప్టికల్ కమ్యూనికేషన్ అవసరం అవుతుంది, బికాస్ వీ నీడ్ టు క్యాప్చర్ ద డేటా అండ్ స్టోర్ ఇట్ వెరీ క్విక్లీ. So that led to the development of optical communication systems, transceivers, optical transceivers. So they'll transmit the data and as well as receive the data. This kind of equipment were developed for storing the data generated in CERN. And further, so next developments were parallel mathematics. Next requirement ఏమొచ్చిందంటే once you collect the data you need to process it. దాన్ని ప్రాసెస్ చేసి what kind of predictions or observations you're going to make is the need of the hour. So దాన్ని ప్రాసెస్ చేయడానికి we have already per second we are going to get zettabytes of data, petabytes of data. సో ఆ ఎక్స్పెరిమెంట్ ఎంతకాలం నడుస్తుందండి? ఒక సెకండ్ కే zettabytes petabytes ఆఫ్ డేటా వచ్చింది. అలాగే అట్లీస్ట్ ఫ్యూ మినిట్స్ నడిచినా కానీ we're not able to handle it. ఈ బిగ్ డేటా అనాలిసిస్ అనే కంప్లీట్ బ్రాంచ్ ఆఫ్ కంప్యూటర్ సైన్స్ వాజ్ evolved just to handle the data of this LHC, linear hadron colliders. Okay, and further other requirements for parallel math processing requirements ఏమున్నాయండి? Like you need a proper processor. The first processor identified for the purpose was GPU, graphical processor unit, where matrices of data is being processed to develop a image. మనకు ఒక 4K లో లేదు ఫుల్ HD లో ఒక ఇమేజ్ ప్రొజెక్ట్ చేయాలి అంటే మనకి ఎలాంటి ఇన్ఫర్మేషన్ కావాలండి? సో వర్స్ట్ కేస్ లో లెట్స్ 1024/768 ఒక మ్యాట్రిక్స్. సో ఈచ్ పిక్సెల్ will have 1024 multiplied by 768, almost 10 power 6 data points ఉంటాయి. Each pixel carries RBG, red, blue, green information, or CYM, cyan, yellow, magenta. 3 data points ఉంటాయి. సో ఆల్మోస్ట్ 3 into 10 power 6 డేటా పాయింట్స్ ఒక్కసారి ప్రాసెస్ అయితే మనకి ఒక ఇమేజ్ అనేది జనరేట్ అవుతుంది, రైట్? సో అలాంటి ఇమేజెస్ ని మనము పర్ సెకండ్ 24 ఫ్రేమ్స్ 50 ఫ్రేమ్స్ ప్లే చేయాల్సిన పరిస్థితులు వస్తున్నాయి. 30 ఫ్రేమ్స్ ఆర్ సెల్ ఫోన్స్ ఆర్ నౌ రికార్డింగ్ 30 ఫ్రేమ్స్ ఆర్ 60 ఫ్రేమ్స్ పర్ సెకండ్ ఆన్ HD క్వాలిటీ ఆర్ ఈవెన్ సమ్ టైమ్స్ ఇన్ 4K క్వాలిటీ. సో ఏం జరుగుతుందంటే, సో we need to these graphical processing units are now able to process huge volumes of data at a time effectively. So these were first chosen for processing this big data generated in CERN. So that is a starting point for our AI or even cloud computing. So and further units like tensor processing unit, instead of matrices, higher order data is tensor. So tensor processing units are developed and AI accelerators. So these are all basically developed for graphical processing and further utilized for big data analysis and AI. And other things are like FPGA gated arrays and application specific integrated circuits, ASICs, and multiplier accumulator units, MAC units. సో ఈ మ్యాక్ యూనిట్స్ అంటే ఏంటి? మామూలుగా అయితే మనకి ఎర్లియర్ కంప్యూటర్ ఒక అక్యుములేటర్ సపరేట్ గా ఉంటుంది అండ్ ఈ ప్రాసెసింగ్ యూనిట్స్ సపరేట్ గా ఉంటాయి. ఇన్స్టెడ్ ఆఫ్ దట్ నౌ పీపుల్ హావ్ డెవలప్డ్ మ్యాక్ వేర్ క్యాలిక్యులేషన్ అండ్ డేటా స్టోరేజ్ టేక్ ప్లేస్ ఇన్ వన్ ప్లేస్, మ్యాక్ యూనిట్స్. సో దీస్ ఆర్ ద డెవలప్మెంట్స్ produced for processing the big data produced in CERN. And next comes the most important thing is this distributed brain system, like neural networks. So manaki aa data so LHC, large hadron collider first start chesinappudu it was started in 2001 and it took 7 years to establish it, and its first process started in 2008. Okay, so process లో people have developed from 2001 to 8 this WLCG, Worldwide LHC Computing Grid. So people have developed a set of systems which can store the data produced, like petabytes of data produced per each second. సో వాటిని అన్నింటినీ కనెక్ట్ చేయడానికి మనకి ఏం కావాలండి? we need optical communicators, optical trans receivers develop చేశారు. And at the same time, cloud computing was the most important to process the data. So the first development related to that was this virtualization. So మన ప్రాసెసర్స్ లో ఇప్పుడు కోర్ ప్రాసెసర్స్ అండ్ థ్రెడ్స్ అని వినే ఉంటారు. ఈవెన్ ఆల్ ఇంటెల్ ప్రాసెసర్స్ మనకి ల్యాప్టాప్ డెస్క్టాప్స్ అన్నిట్లో కూడా నెంబర్ ఆఫ్ కోర్స్ అండ్ థ్రెడ్స్ అని విని ఉంటారు. కోర్ అనేది ఫిజికల్ ప్రాసెసర్, థ్రెడ్స్ అనేవి హౌ సాఫ్ట్వేర్ సీస్ దోస్ ప్రాసెసర్స్. అంటే వీఆర్ నాట్ యూజువల్లీ యూజ్ ద ఎంటైర్ ప్రాసెసర్ స్పీడ్ ఆల్వేస్. ప్రతిసారి ఆ ప్రాసెస్ స్పీడ్ మొత్తాన్ని మనం వాడుకోలేము. సో ఆప్షన్ బి అంటే వెరెవర్ a portion of the processor is empty, we can consider it as a separate processor. So that activity of mapping vacant spaces is done by hypervisor. So it breaks the hardware or shows the hardware as a series of virtual machines instead of a single processor. So manaku oka processor lo suppose you have 2 gigahertz processor, and for a particular application you are using let's say 500 megahertz. So it divides the entire processor into 4 virtual processors and shows you 4 virtual units with 500 megahertz. So ilaga this virtualization technology enabled the development of cloud computing ecosystem. Okay, so that was the major breakthrough which led to the development of this AI and quantum computing, especially AI, where you'll be dealing with huge volumes of data at a time, because so many people will be accessing the same software or same tools which are stored on a cloud. So it has to manage the resources effectively so that will finally achieve most efficient output with minimal resources. So with the development of that, otherwise you would have needed to build kilometers of space to store the data that AI requires. సో అంత మొత్తాన్ని మనము సింపుల్ గా ప్రాసెస్ చేయడానికి కుదిరింది బికాస్ ఆఫ్ దిస్ క్లౌడ్ కంప్యూటింగ్. ఓకే, అండ్ సో టిల్ నౌ we are dealing with only classical data where binary set of information is being processed. So now comes the breakthrough into quantum mechanical world. So the discussion for this quantum mechanical extension started even in 1981, where Richard Feynman declared that we need to build separate quantum mechanical systems to deal with quantum entanglement kind of data. So the first system was developed in 1995 that deals with quantum logic, and it is also developed for high energy physics applications. Okay, and so now this quantum computing is now a reality, whose roots were started in 1981 and first practical application started in 1995. Okay, so from 89 where World Wide Web was developed, early 2000s GPUs were developed, and 2008 LHC cloud computing framework was developed, and finally we are now enjoying this quantum computing and AI tools. So we are going to see a few of the physics concepts that underlie behind this quantum computing. So the first one is this one possible method of storing this qubits is quantum dots, using quantum dots. Okay, so quantum dot and it's a three-dimensional confinement of any particular atom. So when you chop the atoms in all the three directions and to nanometer scale, let's say, you may count it as a particle in three-dimensional box. So manaki one-dimensional box lo elagaithe energy levels untayo, same kind of energy levels you'll see in even in a three-dimensional box. So but the energy levels are degenerate sometimes because of the three dimensions. So మనకు one dimensional అయితే there are no degenerate energy levels, whereas in three dimensions you'll have degenerate energy levels. And as a function of magnetic field, when you apply magnetic field on that system, this degeneracy will lift it up. So you'll have different energy levels. Let's say here you have two energy levels with the same energy, two states with the same energy, and when you rise the magnetic field, this degeneracy will get lifted up. So like that, the function of magnetic field, there'll be a set of energy levels, and we call them as in this case we call them as qubits. So if an electron lies in a particular state, we consider it as one state, and if there are a set of electrons within that quantum dot, so they'll occupy just like you fill a harmonic oscillator energy level or a particle in a box energy levels. The atom or artificial atom, we call this quantum dot as an artificial atom. Those energy levels also will get filled up to certain level, and we call each state as a qubit. So now, with this basic idea, we try to see one most important method of dealing with these qubits. So as of now, I've seen like IBM's quantum computer, 128-bit or even 256-bit, nearly 128 plus. Those quantum computers are developed with superconducting materials. Okay, so they require huge amounts of cooling systems where you need to reach near to 0 Kelvin. Especially to store that quantum information, to store that qubit state intact. So దాన్ని ప్రాపర్ గా స్టోర్ చేయడానికి మనకి నియర్ జీరో టెంపరేచర్స్ అవసరం అవుతున్నాయి. So alternative options, one most important option is this photons. When you deal with light, it is most effective way of dealing with of course it is the most fastest way also even for processing. So one such single photon generators, so we need a single photon generator to start this qubit data to generate single photons. So one such single photon generator is trapped atoms or ions, just like in our laser cavity. If you keep an atom, it will resonate with the length of the cavity. I mean, if you properly choose the length of the cavity, it will resonate at a particular frequency. So you can trap a single photon in that laser cavity and use it as a qubit generator, at the same time qubit storage system also. Simple possibility is laser cavity. And another kind of, just like our sir said in the morning session, Bhagwanaran Garu, so these nitrogen vacancy centers. So these kind of crystals, so these rare earth perovskites, most often will be using that rare earth perovskite for this kind of applications. So when you create a nitrogen vacancy, that acts as a storage mechanism for this photon. So when that photon enters that nitrogen vacancy, that information will be stored as a spin polarization. So it will excite a spin polarized state within that vacancy. And when it comes back, or when you try to retrieve that energy, you'll be able to, when that excited electron or atom comes back to ground state, you'll get back the same photon with the same polarization state. So that is one most effective way of storing optical data. And another one, generating optical data is spontaneous parametric down conversion. So when you give a particular photon in the down conversion process, you'll be able to generate 2 photons with reduced frequency. Okay, reduced frequency means reduced energy. So when you're given a particular amount of energy to the system, it excites and it produces 2 photons with some of the energies. Okay, so you can generate a required frequency photon for the purpose. So that's one way. Another is this quantum dots, where quantum dot is an artificial atom, where you can control the number of atoms or number of electrons, or you can generate whatever kind of atom you need just by tuning the number of electrons in the quantum dot. So when you excite that quantum dot with the photon, and when it de-excites, you'll get back the photon in the same polarized state, either so polarized along x-axis or polarized along y-axis. So మన light ఎట్లాగంటే polarization state గురించి మాట్లాడేది. So when light travels in a particular direction, let's say along x-axis, the electric field vector will have possibilities of orientation anyway perpendicular to the x direction. So electric field oscillations అనేవి x కి perpendicular గా ఎటైనా ఉండొచ్చు, right? So when you resolve that entire area into components, you'll get 2 components, one along x-axis, one along y, another along z. So when the direction of motion of light is along x, we'll have only 2 polarization components, one along y, another along z. So these 2 are the polarized states. When you consider spin, it is spin up or spin down. So they act like bits, 0, 1 states of qubits. Okay, so that is the basic idea of dealing with this. You can use spin, electron spin, just like you use in this nitrogen vacancy centers, or you can use the polarized state of light, or you can use superconducting states. So these are different ways of dealing with qubits. And when you compare, this down conversion method is that works even at room temperature, but multi-photons are produced. So when you are expecting one single photon, you're generating multiple photons here. So that is the one risk factor with this down conversion method. So you need to isolate one single photon, which is required for your data storage or data processing. And quantum dots, these are the most effective methods that people are working now, but they require ultra cold temperatures. So these NV centers, so deterministic data. So you cannot decide the nature of the data here in down conversion, whereas in NV centers, the data quality is 50-50. Whereas in trapped atoms or ions, when you trap a single photon in a laser cavity, that is the most effective method of determinism. I mean, what kind of polarized state you are storing or what kind of polarized state you're dealing with is well defined and intact. It won't change. So this is a trapped atoms or ion is the most effective method, but they require ultra high vacuum. So even a small contamination will lead the destruction of that photonic state. So right now people are working on silicon photonics. So where this photons are being stored in silicon substrates. సో ఇప్పటి వరకు మనము సిలికాన్ నుంచి ఈ ఎలక్ట్రికల్ ట్రాన్సిషన్స్ సెమీ కండక్టర్ మెటీరియల్స్ వరకే చూసాము. నౌ పీపుల్ ఆర్ డెవలపింగ్ సిలికాన్ ఫోటానిక్స్. సో దే డీల్ విత్ optical information storage on silicon lattice. Okay. So now comes the storage part of qubits. So this is the most difficult and research focused area, where I mean we can generate a qubit very easily, but to store it for longer times is the toughest task. So one such storage mechanism is optical cavity, where you can generate a qubit as well as you can store it. Another option is optical fiber loop, where you will send the qubit generated into a optical fiber loop, and it will simply revolving around the loop forever till you retrieve it back. That's one way. Another is atomic quantum memory, where atoms are cooled down, temperatures are reduced down to microkelvins. So then the spin state of the electron within that atom can capture the polarized state of the photon. Another is rare earth crystals. There is whatever NV centers that we're talking about. They can store the qubit information in terms of spins. Okay, and finally generating and storing. So here the issues with these systems are optical cavity systems. They can store the data or retain the data for microseconds. Optical fiber loop also in microsecond scales. Cold atoms also they are a bit better, millisecond scales. And rare earth dope crystals, they can store the data for hours. So that is a most prominent research area, but they require cryogenic temperatures. Right? And spin-based, they are also the same NV centers, spin-based storage systems. And finally, single photon detectors. So once you store the data, process the data, you need to detect the final result obtained. So one such single photon detector is avalanche photodiode, where one single photon will excite an electron, and it will produce an avalanche of electrons. But the problem with this avalanche photodiode is when you have multiple photons coming in, it cannot detect. Sorry, it cannot clearly count the number of photons. And another method is superconducting nanowire single photon detector. So when that photon falls on a superconducting wire, nanowire, what happens at that particular location? It may produce heat, or it may produce an excitation, or it will destroy the superconducting state. So when that photon interacts with the nanowire, it destroys the superconducting state, and at that particular location, resistance changes, and you'll get a spike in the voltage. So when you connect current loop to that superconducting wire, nanowire, you'll find a spike. So you can exactly count the number of photons received. So whatever way, and another method is transition edge sensor, which uses temperature as a sensing element. So when that photon falls on the material, it generates temperature. so that rise in temperature or spike in temperature will be sensed. So this third method is a bit slower method because it has to produce temperature. So SPAD using silicon and using gallium arsenide perovskites. So these silicon based systems work even at room temperatures, but their efficiency is very low, 50 to 70%. And photon number resolving, so it cannot identify the number of photons. And the dead time is in nanosecond scales, 10 to 100 nanoseconds. So once it counts one photon, it cannot count next photon till 10 to 100 nanoseconds. And maximum counting rate is 10 megahertz. So when you invert this dead time, you'll get the counting rate. So 10 megahertz, that is the frequency of the incoming photons. Those many photons it can count within that limitations of dead time. Whereas this superconducting nanowire systems are more efficient compared to this silicon or other materials, but their dead time is a little higher. I mean, they're comparable. So they're more efficient, but you require very low temperatures, microkelvin temperatures. So that is required for superconducting, to maintain that superconducting state. Whereas this transition state mechanism is more efficient, and you can detect or count each and every photon, but the issue is its response time is very high. So for each photon, it has to rise the temperature of the material, and the temperature spike should be sensed. That is a major issue with this TES systems, but they are more efficient, I mean accurate. But the issue is their counting rate is in kilohertz, whereas others have even hundreds of megahertz range. This TES has a very less range. So these are current trends in processing the qubits in the form of optical data, optical qubits. Okay, so the rest of the details we'll see in the other sessions. Yeah. So, any questions or any? Right. So with that, I'm closing the session.
Thank you, sir, for the session.